Okay, we're working through examples related to the problems in one of the midterm tests from the fall semester. So we have this problem. Okay, A is a set of X. Well, I'm not going to read it to you. Okay, what is in this set? Okay, is if X equals the word aardvark, first word in the dictionary back when we had dictionaries that had pages, is X in the set A? Well, X is the word aardvark. X is in the set A, provided it's greater than 5 plus 1, which would be greater than 6. But aardvark is a word. This is a number. So clearly aardvark is not even a candidate for being in this set. But we have a test. The point is that there's a test for whether a given thing is in the set or not. Okay? If X equals 12, is X a member of the set? Well, let's see. Is 12 greater than 5 plus 1? Yes. So X is in the set A. Okay, abbreviating it a little bit, is X is 4 in A. Well, we test it. Let X equal 4. Is 4 greater than 5 plus 1? No. So X is not a member of A. Okay, well, what are the members of A? Now, if we're confining to integers, and that isn't totally clear, but from the context, that's what we're talking about. If we're talking about integers, what integers X satisfy, X is greater than 5 plus 1. Well, 6 is equal to 5 plus 1, but it's not greater. But any number greater than 6 is going to be greater than 5 plus 1. So all the integers greater than 6 are greater than 5 plus 1. All integers greater than 6 are in the set A. So if A is understood, to consist of integers, then A is a set of all integers greater than 6, which is 7, 8, 9, etc. It's an infinite set. And I guess I would put an equal sign there. Okay, similarly, B will be the set of numbers of integers that are less than 9 minus 1, meaning they're less than 8. 8 is not less than 8, but 7 is. So B is going to be the set of integers going all the way to negative infinity, but ending with 3, 4, 5, 6, 7. Now, what is A intersection B? It's a set of all integers depending on how to state this. It's a set of all, integers in both A and B, because the definition of intersection was just this. It's a set of all elements of A that are also elements of B, or alternatively, all elements of B that are also elements of A. Now, what integers are in both A and B? Well, it seems to me that 7's about it. 7's in A, 7's in B, and there's nothing here that's in B and nothing here that's in A. So A intersection B is simply the set consisting of 7. Now, I'll just go on a little further here. Okay. And I think I want to go over here. Oh, shoot. Okay, well, I hadn't recorded this last segment, but I'm going to talk through it anyhow. So, okay, so we've established all this. Now, we go on a little bit. We'll talk about union. Okay, X is a member of A union B if and only if X is a member of A or X is a member of B. Okay, well, what does OR mean? An OR statement, as you know from logic, is true provided both of the things are not false. So if either one of these is true, or even if both of them are true, the OR statement is true. So we can note that 7 is a member of A and 7's also a member of B. Well, since 7's a member of A and 7's a member of B, then the statement 7's a member of A or 7 is a member of B is true. We can say that thus 7 is a member of A union B. Okay, well, the numbers 8, 9, 10, 11, and so forth are all members of the set A, all members of A, taking little liberty with the notation. So they're also members of A union B. 5, 4, 3, and on down. Well, there they are, 5, 4, 3, and I forgot about 6. 6, 5, 4, 3, and so forth are all members of B, all the way down, approaching negative infinity. So they're also members of A union B. Follows that A union B consists of what? Well, 3 is a member because it's in B. 4 is a member, 5, 6 is a member. Those are all in B. 7's in both. Doesn't mean we're going to list it twice. 7's a member. That's it. 7's a member of the set. It's not a member of the set twice just because it's in both sets. So we list 7 once. And then 8, 9, 10, so on. Okay, so that's the set A union B. Okay. Now I want to look at what a Venn diagram of two sets would look like, and what a Venn diagram for these particular sets might contain. Excuse me. So a Venn diagram for two sets consists of a rectangle, usually a rectangle, could be any shape, but traditionally we do it as a rectangle. And then usually a couple of circles. Again, they could have a different shape. So one of these circles represents A, the other represents B. And we have members in different places within the set. Well, where does 5 go? Well, 5 is a member of B and it's not a member of A. So 5 is going to go in this circle for 6 for B. And so's 3. Well, you can see that all the numbers from 6 on down are going to be in B, and they're not going to be in A. So they can't put them here. They're here, they're in the A circle. Okay, so I'll put 6 there, might be a little hard to read. And I'm writing 6, 5, 4, and then 3 dots. This is an infinite set. We can't write them all in there. So I'm using the 3 dots that might have come through well, and they might not have. Okay. In the set A, we have 8, 9, 10, and so forth that aren't members of B. So we have 8, 9, 10, and so forth, not members of B. And then where's 7 going to go? Well, 7 is a member of set A, but we can't put it here in this region because it's also a member of B. It has to go here. Okay, so from this example, we can understand that this set here, this is A, and this is B. This set here is A intersection B. This region here is where the members of A intersection B will go. It's where A and B overlap. It's where anything in here is a member of A and it's also a member of B because it's inside of both circles. And that's A union B. Now I could draw Venn diagrams. I could draw a lot of Venn diagrams, but adjust the camera a little bit. I'm not going to be able to give complete explanations of these things because everybody that's watching this is assumed to have been through the homework in chapters 3 and 2 and done the problems and done reasonably well. Some people very well. There's some people would have 100% averages. Okay. At least on most assignments. Okay. So we got A and B here. And here, of course, we've got A intersection B. And let's say I want to shade A intersection B prime. Now, B prime stands for everything that's outside of B. So B prime, well, I can kind of shade that. So A intersection B prime, I've shaded like this. Sorry, B prime, I've shaded don't like the way that's set up. But I'll just do that. This represents how I'm shading B prime. Now, A intersection B prime is a set of all elements that are in A, not in B, or they're in A and they're in B prime. Okay, so B prime encompasses a lot of things that aren't in A. You know, this whole region out here within the universal set is not part of the set A. The part of set A that intersects B prime is here. So there is A intersection B prime. And it's shaded this way and this way. It's this part of A. Okay, well, if we come back to the Venn diagram then, we can say that here is A intersection B prime. And similarly, we can say that this is everything, well, this region here, bounded by this circle and this part of this circle, is, I'll write it in alphabetical order, A prime intersection B. Everything outside of A and in B. That's here. That would be this section, this part of the circle, part of the diagram. Okay, then this other part of the diagram that's outside of both circles. So what's that? Well, let's look at A union B. Okay, well, it's in A union B if it's in A. Okay, so I can shade all of A. And also if it's in B. Okay, so I can shade all the rest of B as well. And then I can shade all of B, but this part of B, the part where A intersects B, is already shaded, so I don't have to shade it twice. I'll just extend my shading all the way into B. And there's A intersection, A union B. And then this set out here is everything outside of A union B. So it's the set A union B prime. And there we have it. Okay, well, that's a little bit about Venn diagrams for two sets in the shading. If we want to use this set, we see that the set 8, 9, 10, and so forth is which set? Well, it's the part of A that isn't part of B. So in this case, we would say, make sure what have I got behind it. Okay. For this set, is a set 8, 9, and so forth. It's here. A intersection B is a set consisting of 7. Which we already, actually, we didn't do that, but there it is. And I'm not going to, well, I guess I'm getting an arrow into that. I can just jump over this thing and come up here. I jumped the wrong way. Not messing everything up, but there it is. Okay. And then over here, what have we got? Well, we've got set B intersection A prime. So I'm not going to. Set of all numbers, set of all integers up to 6. Okay, so this gives you a little information how you put numbers inside of sets to make sense of how they're related. It's going to be in the test. I almost guarantee it. Okay, so hopefully that's going to be helpful. I'll go on a little bit. I've got to rearrange the boards for a second. And then we'll talk about intersections, unions, and so forth, involving three sets and how you shade them and so forth. Okay, now if we have three sets. We're going to draw the first two sets so that they overlap because in general, well, we have to accommodate the possibility that they overlap. If we're sure they don't overlap, then we could draw two circles that don't overlap. But when we're just looking at general sets, they've got to overlap in every possible way. Well, that's the only way two sets can overlap. Now, if I had a third set, well, I could draw a picture kind of like this. That's three sets, and there's an overlap. But this third set doesn't overlap the first set. They have to overlap. All three sets have to overlap. And every set has to overlap every other set, which incidentally makes it really tricky if you've got four sets. You can't do it with circles anymore. But we don't worry too much about that. Okay, so we have to draw it sort of like this. So now this set overlaps this one, and this one overlaps this one. Now this divides the Venn diagram into 1, 2, 3, 4, 5, 6, 7, 8 regions. Okay, 8 regions. And any set of unions, intersections, complements, and so forth of these three sets is going to be some combination of one or more of these 8 regions. Okay, so okay, any union, intersection, complement, combination of such consists of one or more of these 8 regions. Well, let's let the first set be A, let the second set be B, let the third set be C. Then let's consider, let's say A intersection C prime. Now, A intersection C is where A overlaps C, because A intersection C is a set of all elements that are in A as well as in C. So elements here in this part of A in this region or this region, which is part of A, can't be in the intersection because they are in C. And this region and this region are in C, part of C, but they're not part of A, so they're not included. What is included in A intersection C is this region and this region. So to start saying how this set is shaded, we would shade A intersection C. So let's just make a note that here's A intersection C. Well, we're after A intersection C prime. A intersection C prime is going to consist of everything that's not in A intersection C. So A intersection C consists of these two regions of the Venn diagram. A intersection C prime consists of all the rest of the diagram. So we could shade that by just shading every part of the diagram, every region, except those in A intersection C. Now the white and the yellow don't contrast that well, so I'm going to kind of write over this in blue. So there's A intersection C. The complement of A intersection C is everything else. Okay, what if we wanted to do B intersection A intersection C prime? Now, once more, we would probably start by shading A intersection C to see where it is. And then we get A intersection C prime by shading everything outside of that. And then we would get B intersection A intersection C prime. That'd be everything in B that's also in A intersection C prime. Well, here's B. The part of B that's in A intersection C prime is the part of B that's shaded for A intersection C prime, which is going to be everything in B. We got 1, 2, 3, 4 regions of B, and 3 of those regions are shaded for A intersection C prime. And I didn't. Let's make sure that we understand this. A intersection C prime is shaded in this direction. Okay, now B intersection A intersection C prime is everything that's in B, all 4 of these regions except any that are not in A intersection C, or that are in A intersection C prime. So, well, that's going to consist of everything here, everything except this part of B. This part of B is in A intersection C. It's not in A intersection C prime. Again, to analyze it, start with A intersection C, shade A intersection C prime, and then see where B overlaps A intersection C prime. So, and shade it like this, and right there it is. Now, if I have a set of numbers, let's say that A is a set of numbers 3, 4, 5 up to 11. Well, then all those numbers have to go in the set A. But we don't know where to put them. If there's a set B, a set C, well, let's see. Let's say that set B is a set of numbers 1, 2, 3, 4. And C is a set of numbers 2, 4, 6, 8, 10, 12. Okay, where are these numbers going to go? I'm not sure I left myself room to write them legibly, but let's try. Okay, well, 3 and 4 are in A. They're also in B. Well, let's just take the numbers. Okay, all the numbers are between 2 and 12. Okay, where does 2 go? 2's in C. It's not in B. It's not in A. That means 2 has to go here. What about 4? Well, doggone it, 4 is here, here, and here. 4 is in all 3 sets. So we better have 4 in here. Now I shaded that dark blue. I don't have a good way to write it. Let's see what happens. Yeah, okay. Hopefully you can see that. That's 4. Okay. Now what about 3? Because we're doing these in order. 3 is in A and it's in B. So 3 has to go here. Okay, we've taken care of 4. It goes there. What about 5? Well, 5's in A and it's not in any of the other sets. So 5 has to go here. What about 6? Well, 6 is in C and it's also in A. So we'll have a lot of room in C intersection A. We try to put it in here. It's going to be here. 6 is there. 7 is in A. It's not in either of these sets. It's got 7 here. And 5, we've got 7. 8 is in C and it's in A. And again, I'm not going to have room for it. Let's try. Okay, there's 8. 9 is in A. It's not in any of the other sets. And then we got 10 here. Okay, well, actually, I can read those numbers. So it's there. Because 10's in both C and A. 11 is in A, but none of the other sets. And 12 is in C, but none of the other sets. Now let me draw this set without all the shading. Make my circles pretty big so I've got room. Give them a little more room to overlap. And what we have then is we have set A, set B, set C. We have 5, 7, 9, 11 floating around in A, not in any of the other sets. We have 4 all by itself here in this region. We have 6, 8, and 10, which is probably hard to read. But there we have 6, 8, and 10 in this region. It looks like I didn't notice 1. Okay, 1, of course, is in B and none of the other sets. So you got this here. So now in the part of B, here we've got 1. In this part, where A and B meet, but not part of C, we have the number 3. Down here, we've got 2, 4, 2, and 12. I think that's all our numbers. Let's see how many numbers we've got. We've got 1. Well, let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's all my numbers. Okay. In this case, A intersection C prime is everything that's in A that's not in C. I'm sorry, said that wrong. That would be A intersection C prime, but this is A intersection C, all that prime. Okay, so A intersection C is this region here, as we saw. A intersection C prime is everything outside of this region. Okay, now if it's here, well, I'm just going to write it. Okay, these are the members of A that aren't in where A and C overlap. Okay, and then B intersection A intersection C prime. Well, that consists of this part, and this part of B. Doesn't include this part because this part is in A intersection C. So it's not in A intersection C prime. So that's going to consist just of the 3 and the 1. And there's no number in here. I wonder what region that is. Okay, well, it's in B, it's in C, it's not in A. So this empty region here, I don't have room to label it, but this empty region, I'll write it down here. It's not a good place to write it, that's all I've got. Let's write in words. It's part of B, it's part of C, it's not part of A. So it's in B intersection C, intersection A prime. Well, there's much more to it. And since everybody has done a lot of work on this stuff, this ought to help pull it together. I'm not trying to teach this from an introduction. I'm trying to teach this or trying to help you pull together the things that you've done in in my lab in such a way that you understand how they tie together. Okay. So that's a fair amount about sets, about as much as you're going to want to see before the upcoming midterm, because it's coming up in a couple of days. But this should be, I hope, helpful to you. Now we're going to go on and talk about a few other things. Okay, now let's consider the statement. If it snows, we won't go. Okay, that is a conditional. It's a conditional statement. It's a compound statement of the conditional type, as opposed to disjunction or conjunction or negations and so forth. Okay, if it snows, we won't go. We want to write down the converse, inverse, and contrapositive of this statement. And then we want to do truth tables to test and see which of the 4 statements, the original statement, the converse, the inverse, the contrapositive, might have the same meaning, might have the same logical meaning. Okay, well, the first thing we need to do is P equal it snows, Q equals we won't go. Then we can write the statement. is symbolized like this. Okay, well, let's see. Converse is what we get when we reverse the P and the Q. Inverse is when we negate P and Q from the original statement in the original order. And the contrapositive is what we get when we do both of these things. We reverse the order and we negate everything. So that's going to be reversing the order would give us Q, if Q, then P, and then we negate those. So it's if not Q, then not P. Okay. Now we can do truth tables, and then we write out the statements. Okay. So statements if P, then Q. Well, that's our original statement. The converse is if Q, then P. And this says, abbreviating it someplace, if we don't go, it snows. Okay. The inverse is if not P, then not Q. And I'll say the negation of P, I'm just going to abbreviate that. Negation of P would be it doesn't snow. Don't have much room, so I'm going to write it as briefly as possible, as briefly as I can think. If no snow, then we won't not go. Well, let's stop a second and see. It might have been better to say, okay, then yeah, we can change our wording and our tenses and our grammar just a little bit to take care of negations, as long as this has exactly the opposite meaning of this. It snows, doesn't snow, or no snow. Okay, we won't go is Q. Not Q is we don't. So getting all this out of the way, now we can say if not Q, then not, if not P, then not Q means no snow, then no go. Okay, if no snow, I'm sorry, if no snow, we go. And then contrapositive, if not Q, then not P. Well, that means if we go, then no snow. Now, technically, I don't know if that thing has the right cause and effect relationship, but logically, let's see what's equivalent to what. If I say, if it snows, we won't go. And if I say, if we don't go, it'll snow. Are those equivalent statements? Well, it kind of doesn't feel that way, but it can be a little confusing. That's why we use truth tables and try to get our heads around just what the logical statements mean. Okay. Or what about if it doesn't snow, we go? If I say that, if it doesn't snow, we'll go. And then I say, somebody else says, well, if it snows, we won't go. Those are related, maybe a little confusing, but are they equivalent? Okay. And then here, if we go, then it didn't snow. And this says, if it snows, we won't go. Does that mean same thing as any of the others? Well, let's make truth tables and see how this works. Okay, so we have P, Q, if P, then Q. Very simple truth table. Okay, P could be true, and then, okay, P could be true, Q could be either true or false. Okay, then P could be false, and Q could be either true or false. Those are the only possibilities if P and Q are statements. A statement's either true or false. So if you have two statements, you have four possible sets of truth values. Okay, well, the rule for the conditional is it's true unless whatever's in front is true and whatever follows is false. A false can't follow a true. Okay. Anything can follow a false, but a false can't follow a true. Okay, so we have, well, P and Q are both true, then we have a true following a true. If P is true and Q is false, then we have a false following a true. That's exactly when we can say the statement is false. Now, if P is false, it doesn't matter what Q is, the statement can't be proven false. So we then say it's true. Okay, well, that's this one. Okay, well, let's try P, Q, the inverse, sorry, the converse, Q, then P. Again, we have true, 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 false, false, true, false, false. Okay, now, if Q, then P, well, true and true, the true can follow a true, that's fine. Okay, now, you've got to be careful. Q is now false and P is true. So we have something true following from something false. And yeah, that's not a contradiction. That's okay. But now we have where P is false and Q is true. So now you have something false following from something true, and that's what's forbidden. That'll be false. And again, if they're both false, that makes them true. They want to think, oh, they're both false, it's false. No, that's not so, not logically. Okay, then we have the inverse. And at this point, I really don't want to write a not P, if not P, then not Q statement, where I have to do too much thinking. Namely, I have to reverse the P and the Q truth values and then put them into a conditional and remember how I reverse them and remember the rule for the conditional. That's a little too complicated. So I'm going to have a column for not Q, not P, column for not Q, and then a column for okay, for the converse, if not Q, then not P. Okay, well, P is true in the first line, so not P will be false in the first line. P is true in the second line, so not P will be false. P is true in the third and fourth line, so not P will be true in both. So all we've done is this column reverses the truth values of this column. And if we're careful and do that, we're going to be right so far. And then we reverse the truth values of Q. Q goes true, false, not Q has to go false, true, false, true. So now in every line, the truth value of not P in every row, truth value of not P is exactly opposite to the truth value of P, and the truth value of not Q is opposite to the truth value of Q. So now we can evaluate this. We don't have to look back at the PQ line and think about how you negate them. we can evaluate this just by looking here and here. It's going to be true unless this not Q is true and not P is false. But where does that occur? Well, not Q is true here and here. Not P is false here. It's true here. So here, where not Q is true, not P is false, this makes the contrapositive false. And you can verify for yourself that's the only place where not Q is true and P is false. So all the others are true. And then I want to do the inverse. And actually, I meant to do the inverse here, but that's okay. So the inverse, just trying to figure out where I got the most room. I'm going to lower the camera because Zoom's going to invade this part of the screen with some stuff when you look at the video. So kind of riding uphill here. I got a little more room over here. And I've got the screen low or the camera low enough, so I think I can do this. Okay, so we're going to have P, Q, not P, not Q, and then if not P, then not Q. You have to write things just a little smaller. But we're going to have our true, 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 false, false, true, false, false values for P and Q. We reverse them just as we did up here. We're going to get false, true, false, false, sorry. True, true, and then false, true, false, true. So now all we have to do is identify any set of values for not P and not Q that make not P true and not Q false. So where is not P true? Here and here. Where is not Q false? Here. Okay. So this is where the if not P, then not Q is going to be false. And otherwise, it's going to be true. And now let's look at which, try to get that chalk, which of these have the same meaning, because they're going to have the same meaning if the final truth values are the same. As if two of these have the same final truth values, then they have the same meaning, even if it doesn't necessarily feel like they have the same meaning. Well, you want to kind of think about it so you get a better feel for when things are equivalent. Okay, so let's see. If P then Q, what's equivalent to this? Is anything equivalent to this? Does anything go true, false, true, true? Well, this one goes true, true, false, true. That's not the same. This one goes true, false, true, true. Wait a minute, I think that's it. Yeah, look, same thing. Okay, so this is the same as this, so that these two statements are equivalent. If it snows, we won't go. So the same thing is, if we go, then it didn't snow. Okay. And here and here, we see truth values are the same here and here. So truth values here are the same as they are here. So the inverse and the converse are equivalent. Okay, this is the converse, this is the inverse. And that means to say, if we don't go, it snowed, is the same thing as to say, if it didn't snow, we don't go. And That's not right. Yeah, it is. See, I'm used to this. I've used all this in mathematical arguments for 2-3 centuries now. And still, I have to look at it. Okay, so don't feel bad if you have to. Okay, so that's that. Now, this is a problem that almost everybody gets right if it occurs on the test that you take. So it's not that hard. Make sure you understand it. It's a problem that frequently occurs on whatever randomized test you happen to get. Okay, let's consider a question of this nature. Is A prime intersection B prime a subset of A always true, never true, or sometimes true? Well, one way to answer the question is to say, well, this consists of everything that's outside of A prime if it's also outside of B prime. It's got to be outside of A prime to be in this intersection. If it's outside of A prime, it's not in A. Okay, so one way we could say this is I can say this: X is a member of A prime union B prime if X is in A prime and X is also in B prime. X must be outside of A. So it can't be in A. Follows that A prime intersection B prime is not a subset of A. Now, there are many ways that we could draw a Venn diagram to look at possibilities in a diagram for two sets. Okay, possible Venn diagrams. For A and B, we could have the one we do when we try to be as general as possible, where A is here and B is here. But we could also do one where A is here and B is here, where B is a subset of A. Or we could draw it so that A is a subset of B, or so that A and B don't overlap. Okay. Now, in this case, what's A prime intersection B prime? Well, I'm not going to go through a lot of detail here, but A intersection B is here. A intersection B prime is everything outside of this set here. Okay, there's your A intersection B, there's your A intersection B prime. Or A prime intersection, sorry, I What I did was A intersection B prime, but that's not what we're doing, is it? We have to redo that. Make it kind of clean. Okay. So I didn't shade that right. Yeah, I shaded it right for what I was thinking, but not for what we said. Here's A, here's B. A prime is everything outside of A. So A prime is shaded like this. B prime is everything outside of B. So there's B prime. Now, where do A prime and B prime meet? Well, this region of A is part of B prime, but it's not part of A prime. This part of B is part of A prime, but it's not part of B prime. This region here isn't part of either, because it's where A and B overlap, which is where A prime and B prime don't overlap. So that A prime intersection B prime is where these overlap. So it's where we have this kind of shading. Just make sure we see where that is. I'll add orange shading. So there it is. Now, what's our condition? Is A prime intersection B prime a subset of A? Well, no, there's a lot of A prime intersection B prime that's outside of A. Matter of fact, it's all outside of A. So clearly it doesn't work. Now, if the sets are like this, then A prime, and I'll use the same kind of shading I did before, A prime is everything outside of A. B prime is everything outside of B. And A prime intersection B prime is again where these intersect, but that's just everything outside of A. And it's clearly not a part of A. If the Venn diagram looks like this, then A prime is going to be everything outside of A. Now A is this set in here. And B prime is going to be everything outside of B. But again, A prime intersection B prime is just going to be the part that's in both sets. And it doesn't even touch A, okay? It's not even close to A. It's clearly not a subset of A. And then if you have A and B like this, well, A prime is everything outside of A. B prime is everything outside of B. But A prime intersection B prime is where these overlap. And again, it's going to be here. It's going to look a little different than it did before. but it's very clear it's not a subset of A. It's not contained in the circle that represents A. So it's one statement that we could analyze. So we can analyze it by the definitions of the sets verbally. We can analyze it by looking at Venn diagrams to establish whether the statement is true or not. A couple of definitions. I don't think it's possible to have gotten through the chapters 2 and 3 without encountering these definitions. Let's be sure. Okay, sets of counting numbers. Sets of colon, counting numbers, whole numbers, integers, even integers, odd whole numbers, odd counting numbers. Okay, counting numbers are the numbers you count with. Okay, if you want to see how big your herd is, you start with 1, 1, 2, 3, 4, whatever. Okay, those are numbers you count with. You don't count with 0 because there's nothing to count. However, and there's a whole lot of controversy when people wanted to start including 0 among our numbers. Why would you have a number for nothing? And violated some religious precepts and people got killed over it. Okay, but anyhow, you get the whole numbers if you add 0 in. And of course, that's very important for our place value number system. We needed that 0. Then once you've added 0, you can subtract a bigger number from a smaller number. Okay, now there's no reason you can't, but it didn't make any sense. If I've got 12 goats in my herd and you take 20 out of it, that makes no sense. Okay, but if you start measuring temperature on a scale, you can go above 0, you can go below 0. If it's 20 degrees outside and it drops 30 degrees, what is it? It's 10 degrees below 0 or negative 10. So you get the integers, which go all the way, forever this way and forever this way. Those are the integers. Just making sure we have the definitions. So then we could talk about sets like even integers. Well, we know what even numbers are, 2, 4, 6, 8, so forth. They end in 2, 4, 6, 8, or 0. So the even integers, well, there they are. All the integers, they're even. Odd whole numbers, well, you know what the whole numbers are. You just pick out the odd ones, which would be 1, 3, 5, 7, 9, and so forth. Okay, those also happen to be the odd counting numbers. Okay, if you pick out the odds out of the counting numbers you have. And that makes sense because the only difference between the counting numbers and the whole numbers is 0. 0 is an odd. So this set could represent the odd whole numbers or the odd counting numbers. Now, there are also rational numbers and real numbers and irrational numbers and stuff, and we'll deal with those when we need to. But in most of the problems you're likely to encounter, you're going to encounter these definitions, okay? So you got to know what they are. So about all I want to say about that. Just definitions that you need to understand.